So for the last couple days, you've been working on problems involving sequences, which we defined as an ordered set of members. So we had like a sub 1, a sub 2, a sub 3, all the way out to a sub n, or it could be infinite and it could just continue. Today what we're going to work on is something known as a series. And a series is where you just take a sequence and you add all the terms up. So we would have a sub 1 plus a sub 2 plus a sub 3 and so on out to a sub n, or again, you could keep adding up all of the terms and get an infinite series where you would add up an infinite number of terms. One of the things that you can do when you are trying to find the sum of a sequence and form a series is to use something called summation notation, or it's also called sigma notation because it uses the capital sigma from the Greek alphabet. Now, what it might look like when you have sigma notation is something like this. This is read the sum from n equals 1 to k of a sub n. And all you do is you just substitute in values of n starting at 1 and ending when you get to k. So we would have a sub 1 plus a sub 2 plus a sub 3 all the way out to a sub k. That sigma is what tells you that you are adding. That's what puts the plus in between your sequences. Now, a little bit of terminology. The n variable is called your index. The k is called an upper limit. And the 1 is the lower limit. And today, all we're going to do is work on how to evaluate sigma notation and a few properties using it. Say I want to evaluate the sum from I equals 1 to 5 of 3i. So what we're going to do is we're going to substitute in values from I equals 1 to 5, and it's always understood that you are going to be using integer values. So you can't use sigma notation if you wanted to substitute in like 1, 1.5, 2, 2.5. You always substitute in integer values from 1 to 5. So we would do 3 times 1 plus 3 times 2 plus 3 times 3, 3 times 4, all the way out to 3 times 5. So my lower limit was 1, my upper limit was 5. So we started with 1 and we ended when we got to 5. And now I can just evaluate those and get 3 plus 6 plus 9 plus 12 plus 15, which gives me a sum of 45. Next, let's evaluate this sigma notation. So we have the sum from k equals 3 to 6 of 1 plus k squared. So again, we're going to start with 3, so we'd have 1 plus 3 squared. Then we're going to go till we get to 6. 1 plus 4 squared, 1 plus 5 squared, and 1 plus 6 squared. But again, if we evaluate each one of those terms, we would get 10 plus 17 plus 26 plus 37, and that gives me a sum of 90. Let's look at one last example of the sigma notation. Let's say we want to find the sum from n equals 0 to 8 of 1 over n factorial. Well, that's going to be 1 over 0 factorial, 1 over 1 factorial. So once I expand all of that out, I end up with this set of numbers, which then I can evaluate each of those and get 1 plus 1 plus a half. So once I expand all of them, I end up with this sum. And if I add all that together, I'm going to end up with 2.7, actually approximately 2.71828. And if you remember from when we did our unit on exponentials and logarithms, that is approximately the value of e. And you can actually mathematically in Calculus 2, one of the things that you do is you can actually prove that it will give you the value of e. At the beginning of our lesson, we talked about the fact that a sequence is a set of numbers, but if you add them together, you get a series. If you have a series that has a fixed number of terms in it, so I could tell you that there's 20 terms in that, then that is called a finite series. And when you find the sum, it's called a partial sum. As a matter of fact, this sum would be called the nth partial sum. So that if I added up the first 5 terms, so let's say that ends with a sub 5, then we would talk about doing the 5th partial sum. But if our series has an infinite number of terms, then we talk about it being an infinite series, and we can find the sum of an infinite series, and that's called the sum of the series. So if you're adding up a fixed number of terms, it's called an nth partial sum or a partial sum. If you're adding up all the terms, it's called the sum of the series. Let's say that they ask us to find this sum and simplify it down. Then we would be finding a third partial sum because we are finding the sum of the first 3 terms. So if I expand this out and I put a 1 in the first time, I'm going to have 4 times 1 plus 2, so that's going to give me 6. If I put in 2, 4 times 2 would be 8 plus 2 would be 10. And then when I put in 3, I'm going to get 4 times 3 is 12, plus 2 is 14. And then if I add all that together, I get 30. So we would say that our third partial sum would be 30. Now, if we continued that and it kept adding more terms, we would end up trying to find the sum of the series. And guys, it should make sense that that is not going to have a final sum because I'm just going to keep adding more numbers that keep getting bigger. We can tell this is increasing by 4 each time. So as I keep going out, I'm just going to add a bigger number on. So this won't have like a finite sum where we could say, oh, the answer is going to be like 4,000. It's going to continue to go on and just get bigger and bigger. So it's going to actually go towards infinity. Let's wrap up by considering this last sum. And notice that we go from n equals 1 to infinity. So we're finding the sum of the series. This would be an infinite sum. So let's substitute in some numbers. Put in 1, I get 3 over 10. Put in 2, I'm going to get 3 over 10 squared. That's 100. Then I'm going to get 3 over 1,000, 3 over 10,000, and so on. Let's change these to decimals and see what happens. Well, 3 over 10 is 0.3. 3 over 100 is 0.03. 3 over 1,000, 0.003. We can start to see that if we add this up, look what happens. We get 0.3, 3, 3, 3, and every time I add on another term, I'm going to add a 3 here. Well, that is 0.3 repeating, which is 1/3. So the sum of that infinite series is actually going to give me a number, not infinity this time, but actually gives me 1/3.